quantitative analysis of fault scarp evolution lets us turn landform shapes into timelines of earthquakes. We will build intuition with 3 pieces. First, a diffusion model that smooths scarps over time. Second, cosmogenic exposure dating that timestamps fresh bedrock scarps. And third, how numerical modeling and multiple datasets combine to infer slip history and hazard. Section 1. Morphologic dating with a diffusion model. Imagine an earthquake creates a vertical step. Over time, erosion and soil creep act like diffusion, rounding the scarp. We'll watch a sharp step blur into a smooth S-shaped profile that gets wider with time. The simplest linear hill slope diffusion model says z changes in time equals kappa times the second derivative of z with respect to x. For a step of height h, the solution is an error function profile. The width grows with the square root of kappa times t. We call kappa t the degradation coefficient. Sharper scarps are younger. Rounder, wider scarps are older. A practical metric is slope angle reduction with time. Let's compare the mid-slope angle through time. Initially, near the angle of repose, about 30 degrees. After many thousands of years, the slope is much gentler. How do we turn shape into age? We fit a model to measured profiles, collect several perpendicular profiles across a scarp, then invert for kappa t. We'll show 3 profiles with different amounts of rounding, labeled young, intermediate, and old. The best fit chooses the kappa times t that matches the observed shape. Typical hill slope diffusivity in arid alluvial fans is about 1 to 5 square meters per 1,000 years. A 3-meter scarp might relax to about 20 degrees mid-slope in roughly 10 to 20,000 years, depending on kappa. We write kappa in square meters per 1,000 years, and the fitted degradation coefficient gives age when divided by kappa. Section 2. Cosmogenic nuclide exposure dating of fault scarps. Cosmic rays create rare isotopes like beryllium-10 or chlorine-36 in exposed rock. A fresh bedrock scarp starts its cosmic clock when the earthquake unveils it. We will draw a bedrock scarp face, collect samples at different heights, and plot concentration versus height. Lower samples have been exposed longer, so they often have higher concentrations. If 2 earthquakes built the scarp in steps, we may see a break in slope of concentration with height, revealing event ages and slip per event. By modeling production rates that decrease with depth, and by sampling enough points, we can invert concentration versus height for both exposure ages and slip in each earthquake. Cosmogenic ages calibrate the absolute timescale, which complements diffusion-based relative ages. Section 3. Numerical modeling and synthesis. We now compare scenarios to decode slip history. Suppose a 4-meter scarp formed in 1 big event versus 4 1-meter events. Diffusion smooths them differently. Multiple event scarps tend to show piecewise convex shapes. Knowing slip per event helps estimate earthquake magnitude and recurrence, which feeds directly into seismic hazard. To summarize, diffusion modeling turns scarp shape into a degradation coefficient and relative age. Cosmogenic nuclide dating provides absolute exposure ages and can resolve multiple events. Numerical models synthesize morphology and geochronology to reconstruct slip history and inform hazard. As topographic data and dating methods improve, our reconstructions will only get sharper.